Nuclear energy. Earlier in science courses, you learned about mass. Probably in grade 9 you learned about conservation of mass. Albert Einstein, in his general theory of relativity, told us that mass and energy are really two forms of the same thing. Mass can be converted to energy, and energy can also be converted to mass. You're converting mass to energy right now, as long as you had breakfast today, or lunch. If we have a mass m that's converted to energy, then we can determine the amount of energy E that can be released by that mass. And this is probably the most famous equation in all of physics, which of course came from Einstein's general theory of relativity. E equals mc squared. Just about everybody has seen this equation, but many people don't know what it means. It's all about energy and mass. But what about the c? What does that mean? Well, that's the square of the speed of light in a vacuum, like in outer space. So c, the speed of light through a vacuum, is 3.0 times 10 to the 8 meters per second, or 300,000 kilometers per second. Nothing travels faster than light. Let's look at an example. What is the energy equivalent of a 52 kilogram person? Well, Gus would write down all our given values. So our mass is given 52 kilograms. The speed of light through a vacuum, 3.0 times 10 to the 8 meters per second. And our unknown is energy. Given values, unknown. Now, let's select our equation. There it is. E equals mc squared. And so we'll substitute in the mass, 52 kilograms, and c, the speed of light through a vacuum, and then we'll square that, and we get 4.7 times 10 to the 18 joules. That's a lot of energy. So if we could convert all of the mass in a 52 kilogram person into energy, we would get 4.7 billion joules of energy. That's a lot. We can't do that, though. But what we can do is examine something which we call the mass defect, which happens on a much smaller scale. If we look at the atom, we see that the mass of all the protons and neutrons that make up the nucleus is greater than the mass of the nucleus, which may seem odd. Let's look at a carbon-12 nucleus, for example. In the carbon-12 nucleus, we have 6 protons and 6 neutrons. Each of the protons has a mass of 1.007276 atomic mass units, and each of the neutrons has a slightly different mass, 1.008665 atomic mass units. So when we add all of that up, we get 12.095646 atomic mass units. The actual mass of a carbon-12 nucleus is 11.996709 atomic mass units, or AMU. So where did that mass go? Well, we can't destroy mass, just as we can't destroy energy. But we can convert mass to energy, and that's what's happened. The 0.098937 AMU of missing mass is called the mass defect, and that's been converted into what we call the binding energy of the nucleus. let's have a look at how much energy that is. Again, we'll use Einstein's equation. We'll substitute in our values, and we get 1.5 times 10 to the minus 11 joules, which is a very, very small amount of energy. Not surprising, the nucleus of an atom is extremely small compared to the mass of a 52 kilogram person. Now, this energy that's stored in the nucleus can also be released in nuclear reactions, such as the ones that take place when we see radioactive decay. In this diagram, we see an example of beta minus decay. So carbon-14 decays through beta minus, and we get a nitrogen-14 nucleus emitted plus an antineutrino and an electron. The energy is released in the form of kinetic energy, so that means that these particles are moving, sometimes with very high speed. The three most common types of radioactive decay are alpha decay, beta decay, and gamma decay. And since they all result in the emission of particles, we often refer to them as alpha emission, beta emission, and gamma emission. With alpha emission, a helium nucleus is emitted. So here we see plutonium, after the reaction we're left with a uranium-236 nucleus, and there's our alpha particle. So that's the helium nucleus that's emitted. In alpha emission, we get something like this. So here's our example from the diagram. This should be an arrow, and that should actually be further down. So I'm going to erase that and try again. Alright, so there's our arrow. We call this an equation, although it's not really an equation. It's similar to a chemical equation, but it shows us the results of a nuclear reaction rather than a chemical reaction. Notice that we can see the atomic numbers and the mass numbers. Remember that the mass number is always bigger. The nucleus that we start with is called the parent nucleus. The nucleus that we end up with is called the daughter nucleus, and any other particles are named, obviously, using their names, in this case the alpha particle. So there's our mass number and there's our atomic number, and each one of these elements will have, rather not elements, but each one of these terms in our nuclear equation will have those listed, as you can see. In beta emission, we have either an electron or a positron emitted, and a positron is the antiparticle of the electron, so it has the same mass as the electron, but it has opposite charge. Again, these should be arrows, like so. We'll fix those. So in this case, we see when carbon undergoes beta emission, we end up with a nitrogen nucleus, and in this case, an electron. In the bottom example, we have a carbon-10 nucleus, which produces a boron nucleus and a positron. So one of these is called beta minus, the other one is called beta plus. I'll let you guess which is which. Gamma emission involves, not surprisingly, the release of some electromagnetic radiation in the form of gamma waves, or gamma rays. So after decay has occurred, the daughter nucleus may be in a high energy state and release energy in the form of gamma rays. it would have to be a high energy state because gamma rays are very high energy waves. That's why they're way over here. Very short wavelength means very high energy. So gamma rays are so high energy, or have such a high energy, you don't want to be around them. Gamma rays have the highest penetrating power of all these types of radiation we've talked about. Now, nuclear fission, which is the kind of nuclear reaction we have inside our large nuclear reactors, like the ones in Pickering and Bruce County that produce electricity for us, we don't sit around and wait for this radioactive to decay naturally. We trigger those nuclear reactions by shooting a whole bunch of neutrons into the fuel, or bombarding the nuclei with neutrons rather. So you can see here the neutron will trigger the reaction. And each fission, or each fission reaction, produces one or more neutrons, which then can trigger more reactions. So that's why we often refer to reaction. Here we can see it illustrated in a slightly larger diagram. If this takes place with enough fuel, then it could take place very, very quickly. We don't want to do that in our reactors, though, so we control it, we slow it down. Here's an example. Fix that up with an arrow, and we start with uranium-235 as the fuel. We add a neutron, and we can see that we produce some krypton and some barium, and in this case we get 3 neutrons produced as well. With nuclear fusion, we could also obtain energy by fusing together light elements like hydrogen or helium. With fission, we used heavy elements like uranium or plutonium. If we take the lighter elements and we fuse them together, for example, 4 hydrogen nuclei fused into 1 helium nucleus, some energy is also produced. So that would look like this. Let me get a couple of electrons, rather positrons produced. Positron because we know that that's positive. But here's the problem. In order to force these light nuclei to undergo nuclear fusion, we have to provide a lot of energy. We have to put more energy in to fuse them together than we get out, and that's because they have to overcome the force of electrostatic repulsion. The sun can do that because the sun has such an enormous gravitational field that it has lots of gas and plasma at extremely high temperatures, and so it's easy for the sun. All those hydrogen nuclei are slammed together really, really hard, and so the sun is a giant fusion reactor. But we can't afford to put more energy in than we get out. So far we have not produced a viable fusion reactor on Earth. Later on, when we talk about electricity, we'll talk a little bit more about how we generate electrical power using nuclear reactors. Here's some practice for you in the meantime.